This video will cover synthesis using beta-dicarbonyl compounds. Beta-dicarbonyl compounds are compounds that have two carbonyls oriented beta from one another. For example, the carbonyl on the right is at the beta position relative to the carbonyl on the left. The same is true for the carbon on the left. The carbonyl on the left is oriented at the beta position relative to the carbonyl on the right. Beta-dicarbonyl compounds have their own special chemistry due to the fact that the alpha protons between the two carbonyls are extremely acidic. This is due to the resonance stabilization of the conjugate base. If we deprotonate at the alpha position, we create an enolate that has several resonance contributors. Because this conjugate base is so stabilized, the conjugate acid, the beta-dicarbonyl, is very acidic. For comparison, the pKa of the alpha proton of the beta-dicarbonyl is about 9 to 13, depending on the exact structure. The pKa of water is 16. In other words, the alpha proton of the beta-dicarbonyl is more acidic than water. The enolate ion that is formed upon deprotonation of the beta-dicarbonyl compound is nucleophilic. It can be used as a nucleophile in alkylation reactions, where the enolate is reacted with an alkyl group with a good leaving group, such as an alkyl halide, in an alpha substitution reaction. The enolate can also be acylated, where the enolate is reacted with an acid chloride to produce the acylated product. The mechanism for the second reaction type takes the form of the enolate attacking the carbonyl carbon to produce the tetrahedral intermediate, which then collapses to kick off the leaving group. Remember that typically we show this happening in multiple steps. In summary, beta-dicarbonyl compounds are very acidic, and the enolates formed following deprotonation can be reacted in several different ways to form alpha-substituted products.